Hello, Mr. Fritz here, aka Mr. Desmos Fan, aka Desmos Bro, aka the Desmost man in the world. Let's talk about geometric sequences. A geometric sequence is a sequence in which it is called geometric if each term can be obtained from the previous one by multiplying by the same non-zero constant. Translation: if I were to take a number like 2 and multiply it by a number like 3, I would get 6. If I were to multiply that by 3, I'd get 18, and so on and so forth, and so on and so forth, continuing my sequence by multiplication. This is a geometric sequence. You might also hear a geometric sequence referred to as a geometric progression. And why are these things called geometric? What does this have to do with geometry? Well, the way that I remember this is if you were to think about similar triangles. Here I have a triangle with sides 2, 3, and 4. And if I were to scale that up, let's say by a scale factor of times 2, then I would have three sides of 4, 6, and 8, since all of the sides scale by a common ratio or common factor. This is where geometric comes from. So because I've multiplied all these sides by the same number, it's the same. In the same vein, a geometric sequence continues to multiply by a same number. Let's talk about what an algebraic definition is. We have the set of u sub n terms. The general term u sub n is geometric if and only if the common ratio between u sub n plus 1 over u sub n equals r. This is what we call the common ratio. So with our arithmetic sequences, we were looking for a constant difference or a common difference between two terms when I subtract them. And with geometric, I'm looking for a common ratio between the two. So as an example, if I had the numbers 2, 4, 6, 8, 10, and so on and so forth, here's my geometric sequence. The ratio between these two numbers, 4 over 2, this would be like u sub 1, u sub 2, u sub 3, and so on and so forth. The ratio between u sub 2 over u sub 1 equals 2, and that is the same as the ratio between, let's pick another two consecutive terms. This would be u sub 4, u sub 5. If I divide u sub 5 by u sub 4, this is also equal to 2, therefore this is a geometric sequence. So this is how you can prove that sequences are geometric. Let's talk about the geometric mean. Here I have three numbers, a, b, and c. They are consecutive terms of a geometric sequence. Then I can write an equation. So that must mean that the ratio of b over a, if I divide b divided by a, then that should equal the same thing as c divided by b. Going back to what the definition was of a geometric sequence. So this would have a common ratio. This is like u sub 1, u sub 2, u sub 3. And if I divide consecutive terms, then they should come out to be the same ratio. So if I set up this equation, I can actually rearrange this a little bit. I can cross multiply, and I would get then that b squared equals a times c. If I wanted to solve for b, I would take the square root of both sides. And then I could say that b is equal to the square root of ac. So what do we call this? We said that, and actually technically it's this positive or negative square root of ac, but we'd say that the square root of ac is the geometric mean or average of a and c. So this is like another way of thinking about averages. Typically when we think of the word average or mean, you have been told to add up all the numbers and divide by the number of terms, but there is something called the geometric mean. Geometric mean is just a different type of mean. We are averaging not by adding and dividing, but we're averaging rather by square rooting surrounding terms. So it's a different type of scaling than it is just adding up numbers and dividing. So it's called the geometric mean or geometric average if I do something kind of like this here. And this will be helpful later on down the road when we're trying to figure out missing terms of a sequence and things like that. So let's talk about what the general term formula is for a geometric sequence. I want some sort of an equation that will produce terms of my formula or of my sequence. So I suppose I have some geometric term sequence. U sub 1 is still going to be considered the initial term. That's not different than arithmetic sequences. And we'll call the common ratio equal to r. So it could be a common ratio of 2, it could be a common ratio of 1/2, it could be a common ratio of 0.001, it doesn't really matter. It's just some constant multiplier. And as we go through this, I've kind of put some numerical examples just to kind of consider down here below. Here you can kind of see that my first term is 2 in this example, and then my common ratio r looks like it's going to be 5. So in this example, u sub 1 is 2, and 5 is my r. So in general, I could say that u sub 2 is equal to u sub 1 times r, and that should make sense. Since 10 in my example with numbers here is 2 times 5, which is my r, I could say then that the third term is equal to u sub 1 times r squared. And let's think about what that means. This third term here, u sub 3, is equal to 2 times 5 times 5. Well, that's another way of saying times 5 squared. So how do I get from u sub 1 to u sub 5? It holds true that I multiply u sub 1 times r squared. And then similarly, I would say that u sub 4 is equal to u sub 1 times r cubed. If I want to get here, I can multiply u sub 1 by the common ratio, in this case 5, 3 times. So that would be times 5 times 5 times 5 times 5. So or r to the third or 5 to the third would produce this value right here. So here's the link that I want to draw between what's going on here. If you take a look, if you compare the number of the term that I'm looking for and the exponent of my r, there is a direct link. What's happening here? I guess there's a missing 1 here, but it's implied. And then I could draw a connection between the 4 and the 3. What's staying the same is u sub 1 is in all 3 of these equations. That doesn't change. We're always going to use our first, we need to know what our first term is in the sequence, always. But how do we generate more terms? Well, it's going to be directly related to the exponent that I use for that common ratio. And hopefully you're seeing there's always a difference of 1 between these two things. So I can generalize this and say that the term that I'm looking for is equal to the initial term times the common ratio raised to the n minus 1 power. So the n is the index just as before, or it's the number of the term. So if I'm looking for my 5th term, I'm plugging in 5 for n. If I'm looking for my 25th term, I'm plugging in 25 for n. And that'll help me generate u sub 5 or u sub 25 in my example. So now we have this general formula. We can generate terms of a sequence, and we can figure out formulas for sequences, and we'll do a whole bunch of that stuff with that in the next video.